being aware that this is the last talk, I tried to use the day to make it fluffy and have a talk to everybody in the room, also the people not working on Rocq. Actually, I think there's 0 lines of Rocq, and more or less, I try to make it applicable to any proof assistant, modular the parts that are not applicable to any proof assistant. Right. So my name is Yannick Forster. I'm now here in INRIA Paris. However, most of this work was done while I was a student and PhD student in Germany, and we had like anonymous reviewers who are also based in Paris, who nowadays call this the Saarland approach to computability theory. So I kept the Saarland University owl, even though no Saarland University is on there, but like credit to the place where we all were at some point, and did all of this work. When I say we, I mean like this has been work that has been going on in different incarnations for at least 8 years. What I'm talking about today was crucially joint work with Dominique Kirst, Gerd Smolker, Dominique Larcher, Won Ling, and André Dudenhefner. And then there's lots of other students and people who might come up during the talk that also contributed. And okay, I'm going to give the overview talk of these things. The lead question kind of the talk, even though that's not really the interesting thing to discuss, but still, that's like the interesting stuff from the perspective of proof libraries is at the end, but in the beginning, this is the lead question, is how to formalize textbooks on computability theory, because at the end we want to talk about the library in proof assistance that can talk about computability theory or that can talk about undecidability proofs. And then more particular, we will spend some time on trying to understand why is this area particularly hard to formalize, again, to be informed on how to build libraries, again, to be informed on how this stuff we did here over the years in Rocq could be done maybe in other systems. Right. If you remember your course on computability, if you ever had a course on computability, and if you remember this course, more or less, this is the table of contents for any textbook on computability theory. Like it's always the same, doesn't matter who wrote the book. Authors start by introducing their favorite model of computation, and the Turing machines, lambda calculus, mu recursive functions, some while-based assembly language, imp, whatever. Then the first thing they prove is the SMN theorem, which in modern like functional programming terminology is currying. Then they argue that there is a universal program. By argue, I mean that probably nobody actually spells out the thing. Certainly nobody proves that it is a universal program, but like the concept of a universal Turing machine, a universal recursive function, in a universal lambda term, those are important concepts. And then this is a bit optional. They introduce a second model, and then they argue that the two things are equivalent. Again, no proofs, but a bit of an intuition that actually it doesn't matter so much what you use as a definition of computability, leading to this concept that actually computability, and this is true and has been true for like 100 years, that actually computability is an intuitive concept, especially nowadays for people who program, but already before we know what it means to be computable, kind of. And then leading to the Church-Turing thesis, saying that everything that is intuitively computable actually can be formalized, can be spelled out in the previously introduced model of computation. And then all of these books play the same trick. They don't actually talk about models of computation anymore. Like once you have the Church-Turing thesis, at any point where your formal proof obligation in the textbook is prove it computable, you say by intuition, done. Maybe there's a bit of text, but like that's the whole point. And this is, it's super successful in the sense that you can teach to students interesting structure of computability, interesting arguments, because you don't have to go down to the assembly level of your proofs. Same in research papers, like people publish decidability and undecidability proofs, still at conferences, and still they will not spell out the Turing machine. Maybe they will not even spell out the program in any programming language, like you spell out the algorithm intuitively, and then again, Church-Turing thesis, done. On this, in the textbooks, you start by the undecidability of the halting problem or the self-halting problem and then halting problem. Fairly easy. Usually people have Rice's theorem, then some reduction theory. It depends a bit. Mahel isomorphism theorem, maybe post-simple and hyper-simple sets. Then, and That's in the textbooks, but not always covered in undergraduate computability. But still, you will have some Oracle computation, Turing reducibility, Kolmogorov complexity, or some other notion of information theoretic complexity. And then maybe something like Klini-Post or post-hierarchy theorem, talking about hierarchy of classifiability, the arithmetical hierarchy, these kinds of things. And then authors prove the undecidability of concrete problems, depends a bit on the taste here, post-correspondence problem, context-free grammars, something like Entscheidungsproblem, satisfiability, validity of first-order formulas, these kinds of things, right? And then I want to emphasize that all of this stuff really relies on the Church-Turing thesis. Once you want to spell out the Turing machine that does the reduction from Turing machine halting to the post-correspondence problem, like your lecture is immediately over and you spend all following weeks on like spelling out this Turing machine. So nobody does it. All of this crucially relies on the Church-Turing thesis. And this has been a successful concept of using this intuitive thesis. Right. Now turning to, only the title changed, turning to computability proofs machine-checked in proof assistance. This is such basic stuff that essentially every proof assistant has a development of some kind of computability theory. And I actually think every model of computability has been at least written down in every proof assistant by now. The earliest, so this for sure, and then still every proof assistant has a formalization of the SMN theorem. And I actually think this is usually stuff that happens fairly early. The first formalization in Rocq is, I think, from 91 or something like this. And same for other systems. In every system, somebody has sat down and dealt with the difficulty of proving the SMN theorems. Arguing a universal program and introducing a second model and arguing their equivalence has been done in many proof assistants. Usually, that's why I didn't put the green check mark. Usually authors write an explicit line that this was very painful and they would recommend nobody to ever try this again, but like we have universal Turing machines, different proof assistants. And I think every proof assistant has at least one universality proof for some kind of language. Then when you work in proof assistants, introducing intuitive computability in the Church-Turing thesis is not an option. Like naturally, the whole point of intuitive computability is that it's intuitive, and like Church-Turing thesis talks about intuitive computability. So no way. Undecidability of the halting problem, really spelling out all the things, no big deal because it's like largely a logical paradox and not really something about computability. Yeah?
But then an equivalent of Church-Turing thesis in a constructive type theory would be to say I can turn my program into a deep embedding of the same program.
Yes, indeed. For now, I don't want to go this route because I want everything to be applicable to all proof assistants. But like, yes, I will talk about this.
Oh.
Then you have Rice's theorem, which has been done in every proof assistant. The proof is not super hard. Like Rice's theorem is a thing you can explain easily, and the textbook proof is like a 10-liner. In a proof assistant, it becomes a bit tricky. And then like reduction theory, Oracle computability, concrete undecidability proofs. By now the slide is getting a bit old because I'm saying we don't know. Well, we know, that's the whole point of the talk. But before we started this work, this has not been done. And now it is in the library, but it requires a bit of an idea that goes in this direction. Right, okay. To explain a bit the difficulty, this is the proof of the SMN theorem. Oh no. This is the proof of the SMN theorem in the book by Rogers. Now it has 3, 6, 7, 8, 9 lines of, don't read the text, 9 lines of text. And crucially here, it says one stands by the Church-Turing thesis, something, and then everything is good. And then he says below, the informal argument by appeal to Church thesis can be replaced by a formal proof. And I messed up my slides because in this line it says in which book. Namely in the book by either Davis or Klini. Now, if you go to the book by Davis, this is a fully formal proof, and it already reads like this, fully formal in the sense that he spells out all the details. I think there's a difference that Davis uses Turing machines while Rogers uses real recursive functions, but okay, whatever. This is more or less how an on-paper fully formal proof looks like. And then I said the SMN theorem has been formalized in every proof assistant. The Isabel proof looks like that. So you can see a bit this progression of like something entirely trivial where you said like a couple of light words and then students believe it, something way more technical if you spell out the details, and something super technical if you need to do it in a proof assistant. That's like lemma 1 of computability theory. And then from there you do the actually interesting stuff, where interesting stuff is if you spell it out, kind of blurred a bit by all of the details. Andre Bauer has coined this notion of invisible mathematics, the mathematics that stays invisible on paper, that's there, but that nobody actually spells out. If you work in a proof assistant, your invisible mathematics usually becomes visible. Like you see all the gory details. In computability, there's a lot of gory details because you have to spell out programs in a model of computation, and models of computation, Turing machines, for instance, are not exactly pretty structures, right? So one way to go is to say, well, if this is so ugly, let's not formalize computability proofs. Maybe this is such a basic topic that mistakes don't happen. So at some point I took the exercise, which is fun, which I recommend to everybody. And I tried to go to the literature and I tried to find all the mistakes in computability theory that are nice to explain in a talk. The one nice one is from 1932. Gödel gave a decidability proof for this fragment of first order logic, like whatever that means, it's a certain fragment of first order logic. And then in the last sentence of the paper, he says, without proof, but like in an authoritative way, this can be extended to include equality. Then lots of people published results depending on Gödel's claim, because Gödel, for instance. In 1984, Will Goldfarb was tasked to prove Gödel's claim as part of his PhD thesis, and then his PhD thesis is about the undecidability of this fragment, because when it turned out that's exactly the boundary on this bit, like indeed the one without equality is decidable, but the one with equality is undecidable. All the people who depended on Gödel's claim had to fix their proofs. I think nothing went wrong in the follow-up results. Like even though the proofs were invalidated, no theorem relying on Gödel's, not actually a theorem, just claim were wrong. So, okay. Completely different topic. 1988, Fiori, Turin, and Urgichin proved the decidability of semi-unification. Semi-unification is a natural thing that comes up in type checking functional languages, simply like type inference of functional languages. And it's something related to unification, but it doesn't matter. It was super hot at the time. Lots of people were tasked with proving the decidability in their PhD thesis and things like this. There were several proofs, but I think the first one was at Poppel by Fiori, Turin, and Urgichin. Then follow-up work at LIX 1919, Fiori, Turin, and Urgichin proved the undecidability. And they have a line in the paper where they say, it turns out that lots of groups of people had proofs of decidability. One of them was ours. It was wrong. It was wrong. We now have a proof. We have a proof of undecidability in Rocq. So like already after people were convinced that the decidability proofs were wrong, the problem is actually undecidable. It's nice that they fixed their own problem. They also got a Poppel and the LIX paper from it. Different story, 1967, the famous book still by Minsky on computability. Minsky introduces two counter machines. And here I need to read from the slide because otherwise I mess it up. With an increment, you have two counters, like they can contain natural numbers. You have an increment operation that increments one of the counters, and then a decrement operation which jumps on 0. Natural idea. Then he writes 200 or so more pages in the book. And then he says, let's go back to two counter machine halting. We now prove it undecidable. He does an undecidability proof. And if you really read in the undecidability proof, you see that he works with increment and decrement where the jump is on non-zero. Tiny difference, but like basically the same thing. Apart from the fact that in 2022, André Dudenhefner proved that decidability of two counter machine halting with increment and jump on 0, how it is defined in the Minsky book, is actually wrong. Again, I try to find, and two counter machine halting is the super famous starting point for undecidability proofs. I did not find a single result that was wrong because of this, which is in a sense a bit sad. And also good. I found lots of proofs that are wrong, but they're all easily fixable. Like all of the proofs are flexible enough so they can go to the actually undecidable non-zero variant and don't stay on the zero variant. It's actually with like 3 minutes of time nice to explain why one of them is decidable and why the other one is undecidable, but not now. All right. Credit where credit is due. Again, computability is a super old topic, super interesting. People understand it. So lots of people have formalized it. I think the first kind of complete formalization that has a universal machine and that has Rice's theorem is 2011 at ITP, I think, in HOL4 by Michael Norrish. In 2017, I did this using lambda calculus together with my supervisor Gerd Smolka in Rocq. Then 2019, mu recursive functions in Lean by Mario Carnero. PVS has a formalization of PVS0, which is some kind of model of computation, also has Rice's theorem. And then there are more like random results. 2019, a group of people proved Hilbert's 10th problem undecidable in Isabelle. With Dominique Lachey, we also have a proof of this in Rocq. 2021, Fabian Kunze, Leonard Gehr, the Cook-Levin theorem, saying that SAT is NP-complete, something like this in Rocq. Super hard work. You need to formalize lots of reductions about Turing machines. You need to formalize the time complexity of these machines. In 2021, with Fabian Kunze and Maxi Wuttke, we have a proof of the polynomial time equivalence of Turing machines in Pointer value lambda calculus, mainly carried out by Maxi Wuttke. Painful stuff, but an equivalence proof. 2023, there was also a proof of the Cook-Levin theorem in Isabelle. For proofs, remember the problem is informal proof, formal proof, machine check proof. You get this explosion in complexity because of all the hidden details and these things. And now we get to the point where we try to say, okay, how to solve this problem without just dying in the details. And to do so, we need to quickly talk about the word synthetic mathematics. You can immediately forget about this again afterwards if you want, but still I want to make this distinction once. Here. Regular mathematics is analytic. That's like an old word from philosophy, but it has been established as a technical term here. Don't think too much about the actual term. Analytic mathematics, I don't think it's a good term actually. Analytic mathematics, the mathematics we all do. We have objects of the logic. If you work in set theory, that's going to be sets. Model the structures under investigation. You write down with the Turing machines, you say, first at some point you say what it means to be a tuple. Then the Turing machine is going to be a 5-tuple of an alphabet that's finite, so you have to say what it means to be a finite set. And a tape, like a configuration is a tape, so you have to say what is a tape, and these kinds of things. But like really, you decompose a definition into its building blocks down to the assembly language of your logical foundations. In synthetic mathematics, you take the objects of the logic and you turn them into the structures under investigation, either mentally or explicitly through axioms. The fine print says that this is only possible in computational systems, in constructive systems, not in all systems. I think we had talks today about Rocq and Lean and Isabelle. It's straightforwardly possible in Rocq and Lean. In Isabelle, we get to this in the end, you have to work harder. But Rocq and Lean are built on a tight theoretic foundation, which allows playing tricks like this, where you can just say, all of the functions I care about are the computable functions, and then you roll with it. And that's a bit like, there was the question by Cyril earlier. So remember the Church-Turing thesis, the power horse of computability theory, says that every intuitively computable function is, let's say, mu recursive, some model of computation. Now, if you cannot use this formally, you have intuitive computability here, but there is a thing that can kind of be taken as a replacement here. Namely, when you work in a system like Rocq, like Lean, whenever you can define a closed function f from natural numbers to natural numbers, like definition f, def f, not the variant where you write non-computable in Lean, but like really the thing you define. It's true, it's a meta theorem that one could actually have defined a mu recursive function computing f. That's a well-known fact about computational constructive systems from like the 40s. And then as a proof rule, it reads, if in the empty context, you can, like no free variables, you can define an f, then actually in the empty context, you can prove the statement there exists a mu recursive function. Like meta theoretically, that's true. We know that every lean program you can define is actually a program, like it's a programming language. Thus, there will be a mu recursive function Turing machine, whatever that computes it. This might be a bit tricky, but like on the high level, that's the whole point of using programming languages to formalize well, stuff. All right. Once you move into this idea, your definitions become easier. Again, that's a thing that's very natural, and that happens in like all, like be it math comp, be it mathlib. There will be a notion of decidability somewhere where you say a predicate, okay, like we work with predicates because it's type theory. It doesn't matter, it could be sets. I write P of X, I could have written X and P, same thing. If you work in analytic computability, you say a set P is decidable if you have for all X P of X if and only if F of X equals true, where F is a total function returning a Boolean, so either true and false, and it always has to return. And then you say, and F is computable, which is a notion that's defined using Turing machines, mu recursive functions, whatever. If you write in this synthetic alternative, you just say this function exists. You don't say anything about its computability because you know you're working in a system like Rocq and Lean where everything you define is actually computable, can actually be executed. You can do the same trick with semi-decidability, which requires some notion of partial functions, many one reducibility, truth table reducibility. Like you look at the textbook definition, you massage it a little bit, you cross out the is computable bit, and you have a nice definition that's going to work in your proof assistant in principle, because they are programming languages in this case. Right. And then you can prove nice theorems. Don't actually read the theorem, but you can play nice tricks that I don't want to go into detail, where you read textbooks on computability and then you actually get theorems about the logic of your proof assistant, because you can use the proof in the proof assistant. But what I really want to talk more about, is about this trick of using this meta rule that everything that you can define is actually computable. It's called Church's rule, like in the work on logic in the 40s. I think Leany invented the name. And we can talk a little bit about why this works, but more particularly why this doesn't work in other systems, why this doesn't work in set theory, in classical set theory, for instance. And the whole point is because in set theory, the characteristic function of, say, the self-halting problem is not mu recursive, it's not generally recursive. And you can write it down. In set theory, you can write down the function. If the nth mu recursive function on input n terminates, then return 1, let's return 0. That's just a function. And if you make it a bit more formal in ZFZ theory, it's going to be the graph relation of this function, because that's what the function is, and it relates n to 1 if this predicate holds, and it relates n to 0 if this predicate holds. It's very easy to show that this is a function in the sense that it is functional, like nothing to prove, and it is fairly easy to show that this is actually a total function. The totality proof requires a bit of classical logic, proof by contradiction, law of excluded middle, but very basic, no problem. Then you have proof that you have a total set theoretic function, and you have defined it in a closed context. That means Church's rule is not true for a system like ZFC, because I can write down this function, and I can clearly not write down a Turing machine that corresponds to deciding the self-halting problem, exercise number 1 in computability. Right. In constructive systems with a constructive background, in computational systems, even something stronger is true. Not only is this meta rule true, you can even write it down as a formula. Every function is computable, and still you're not in trouble. The point is that the functions are a bit of a different thing because they're more computational, but we know it for Heitinger arithmetic by Kleene. There was a whole school of Russian-style constructive mathematics that used this as an axiom built in. We know that any system that has semantics via topoi, there's the effective topos by Hyland that proves this consistent. There's homotopy type theory where it was proved consistent by people. There is Martin-Löf type theory where Pierre-Marie Pétrot proved the thing consistent recently. All right. To get a bit more intuition why this actually works, let's look at the kind of simple slogans of both Rocq and Lean's type theory. One important bit is that types and functions are native. So you have inductive types, natural numbers, Booleans, pair types, and things like that that you build natively in. And then crucially, the function type consists exactly of programs in a total strongly typed programming language. Like that's the idea of type theory. The functions are exactly programs. And then propositions behave constructively in the sense that propositions are types, proofs are programs. That's why they behave constructively. If you want to define total functional relations, you can do that. They're going to be things from A domain to B codomain to the universe of propositions. And then you can do classical logic. There's no problem. You just assume it in line 1 of your development. Double negation elimination, law of excluded middle. Lean more or less does this in like line 1 of mathlib batteries, whatever. The law of excluded middle is assumed derived. And then you roll with it. The relevant bit is, for all of these systems, propositions are types in a separate impredicative universe of propositions. Like you have this type prop that contains all the propositions, and they are not regular types. You have to be a little bit careful if you want to do case analysis on a proof. If you want to do a computational case analysis on something that lives in a type that is a proposition, not everything is allowed in any of these systems. Otherwise, you're inconsistent. Like without any classical logic or whatever, it doesn't work. So for design reasons in the system, you have to set up the system in a way that you cannot do a computational analysis on proofs. Now, this actually will help us a bit to do computability theory, right? If we go back to the question why you cannot just break Church's rule in proof assistant, in these kinds of proof assistants, in these kinds of computational systems, if you want to implement this function in either Rocq or Lean, where you do the if, it's not going to work because you need to write down a computational decision procedure for the self-halting problem. Like that's what you need to do when you do a case analysis. The whole point is this decision cannot be implemented. You cannot write down a function that decides the halting problem. This, like kind of by contraposition, the Church rule is perfectly fine because everything you can write down is exactly the things that are computable. What you can do, again, in all of these systems, is you can define the graph relation that relates the index of a Turing machine to the Boolean that indicates whether it's self-halting or not. Like easy to define. And you can still prove that this is a functional relation, no problem. And again, like in set theory, when you want to do the totality proof, you need some form of classical logic proof by contradiction, law of excluded middle, whatever. Again, no problem, you just assume classical logic. And you can be happy. However, even like this, if you have a functional and total relation, this does not give you a function in the type theoretic sense yet. There's a bit of a gap in between. You cannot just escape the proof world into the computational world in none of these systems just like that. The reason for this is how propositions are modeled and how existential quantifiers, it's not spelled out, but like a totality proof is an existential quantifier, how existential quantifiers are modeled and what the system allows you to do with an existential quantifier. In particular, you cannot turn every totality proof for a relation for all A exists B into a function witnessing this, at least not like this for free, because that's more or less the axiom of choice. It's a variant of the axiom of choice. And again, no system builds this in. I will not go into the explanation why here. Yes, I don't show the rest of the slide. But no system builds this in the sense that you can actually have a function here that you can use in a definition. Mathlib assumes very early on the axiom of choice, but it assumes it as a proposition, and only in proofs you can use the axiom of choice. You can still not use the axiom of choice to define a computational function unless you say non-computable. But if you don't say non-computable, everything fine, everything has to compute. You cannot just do like reference to some magic given from the outside. And this is the thing that's exactly missing. Like this is the thing that would bring you from being able to write down every single function, including a decider for the self-halting problem. But you don't have it in any system in the most general form that you would need. There's a bit of explanation here that we can go to later. And there's more stuff if you want to ask questions, but I don't want to go into detail. The stuff I want to mention, however, is if you work in type theory, airborne type theory, first no assumptions, just CIC, you can have a couple of things consistently living next to each other. You can have Church thesis, like really the axiom stating that every function is computable. The law of excluded middle, classical logic, as one would like. Function extensionality, propositional extensionality, and thus proof irrelevance next to each other. And the axiom of choice in its strongest possible form, but only for relations, where you say every total relation contains a total functional subrelation. Next to each other, they are perfectly fine. Every function that you can actually write down in the function space will be computable, because these things here only give you logical power. And we have this operation between the logical layer and the computational layer in these systems. Cool. Now we can use this, and we have used this in the past to formalize computability theory in Rocq. And well, I chose this for good reasons. We can go through all of these things, and we have built kind of a library of computability proofs working explicitly with these axioms. Whenever we have to write down a Turing machine, we just say church thesis, I wrote down a Rocq function, we're good. And then I want to talk a bit more about undecidability proofs. I think, yes, that's exactly the point, because this is kind of, that was the starting point a while ago. And it's also the biggest library. So mainly this was done from 2017 to 2022. That was the main time where we worked. I think we have like 15 or so contributors. Most of them were either bachelor's or master's students at the time when they contributed. And then the idea is as follows. Yes, let's try to go into the idea. If you do the analytic definition, like regular definition of what it means for a predicate to be undecidable, you say, well, undecidable means there does not exist a mu recursive function which decides it. Undecidable means not decidable. Yes, no surprise here. And then you have a lemma that, for instance, you prove that there is no mu recursive enumerator for the complement of the halting problem. And then you have a theorem that then actually you use all the time. Namely, you prove that if you can many-one reduce the halting problem to a problem P, then that means that P is not decidable. And that's how decidability proofs in practice work. Whenever you want to prove a problem undecidable, then P is not decidable. Whenever you want to prove a problem P undecidable, you actually reduce it from a known undecidable problem to your problem P, and then you publish your undecidability proof. The thing is that this trick also works to do undecidability proof in proof assistance. Until now, we have only explained positive things, like why can you do decidability? Undecidability, it's not so clear, but using this, you can also do undecidability. The reason for this is, well, one, you can just go into an axiomatic context where you assume everything is computable, that works, but you can also then use this intuition in a completely axiom-free context and define a problem P to be undecidable if you can write down a computation that reduces the complement of the halting problem to P. You will have to manually check that the thing you wrote down is actually a program. In Rocq, that's guaranteed. In Lean, you have to double check that it doesn't say non-computable or whatever. But if you can do that, you can do undecidability proofs there. The trick is to make the content kind of positive, explicit by reduction from undecidable problems. This works super well. Let's see what the timing says. This works super well. If you know your computability theory, you know that not all proofs are by many-one reduction. This is true. There are problems that are provably not undecidable by many-one reduction. I have a slide on this that I don't want to explain. I want to go one step back, however, and I want to explain this. There is deep reasons why this works in type theory. They are not related at all to formalizing computability theory. Like that's not what people cared about. But when people designed these systems from the beginning, Cocon, Huet, they were designing these as programming languages. Like it was explicit about programming, and there was explicitly the idea that the proofs are not supposed to be executed. You want to have the programming parts that are supposed to be executed and the proofs that can kind of go away. First PhD thesis by Christine Paulin, extraction of programs in the calculus of constructions, and then 1989 is what it says. And then 2004 PhD thesis of Pierre Letouzy, extraction from CIC with inductive type supervised by Christine. Those are kind of the foundational works that are still used in Lean and compilation to C in extraction to OCaml in Rocq, these kinds of things. The point is that whenever you have a total programming language, you actually are a system for constructive mathematics, and you can then you need this for execution, but also you can use these tricks to play tricks of constructive math that people know from the 40s to do elegant formalizations of, for instance, computability in this case, which is cool. Right, I'm skipping this one, and I want to talk briefly about this undecidability library, which is now a big library with lots of things where we have formalization of undecidable problems, basically all of them by many-one reduction. So you start by the halting problem for Turing machines. We have an equivalence proof of Turing machines and lambda calculus. In particular, you have an equivalence of the halting problems. And then you can reduce to some kind of stack machines, counter machines, Minsky style, Fractran, a la Conway, a bit of a complicated reduction to Hilbert's 10th problem, solvability of Diophantine equations, halting problem for mere recursive functions, and all the way back to lambda calculus. Up there, you have more things around string rewriting. Here, famous problem, and then we go to modified post-correspondence problem and post-correspondence problem, which leads you to problems in first-order logic, but which leads you also to problems in context-free grammars. So we have all the stuff around this. And then the red stuff is things where I never actually was involved and other people picked up the work. Most notably, undecidability of unification problems, higher order unification. There's linear logic stuff here. There's inhabitation of system F, which was a famously hard problem, which corresponds to provability in some higher order logic. Here, typeability of system F. Here, the semi-unification that I mentioned earlier. Probability in something like ZF, finite satisfiability of formulas, things like this. More or less, we are at the point where I think basically whenever you want to have a standard undecidable problem that's kind of well known as a starting point of a reduction, it should be in the library. Apart from tiling problems, where initially there were formalization issues, and now we just, if somebody wants to do tiling problems, we need tiling problems. It's around 100,000 lines of code, 14 contributors. In total, the kind of working mode that I want to advertise is if you want to formalize an undecidability proof, you look at the problems that are very easy starting points of reductions. Halting problem for instance, single tape, two symbol Turing machines. No need to deal with more symbols, no need to deal with more tapes. Post correspondence problems, a couple of other ones. We also have a couple of decidability proofs in there, just to draw the line to say, like, careful, you cannot simplify more here. And then the hardest ones, I think, are Hilbert's 10th problem, joint work with Dominique, higher order unification, which was done by Simon Spies mainly, and then semi-unification, subtyping and type checking in system F, and lambda definability, all by André Dudenhefner, considerably simplifying the paper proofs. There's a big library of stuff around first order logic, where I will not read, mainly driven by Dominique Kiers, which is also very connected to decidability and undecidability proofs. And then lastly, we have a lot of stuff around models of computation. One, we have this equivalence for computability of all of these notions proved in like all of these models of computation. If you really want to work in a model of computation, I think that weak call by value lambda calculus is the sweet spot. That means essentially something like OCaml standard ML. Well, lean if you want, but as a model of computation. For this, we have an ad hoc extraction framework doing automatic computability proofs if you're lucky, and then it can be used to prove many one equivalences between problems, so like really formalizing the many one equivalence using a model of computation. This even works as a foundation for analytic complexity theory, which was a line of work pushed by Fabian Kunze that also led to the Cook-Liebman theorem in Rocq. However, and there's a problem, a good framework for automatic computability proofs is missing in our setting and in any proof assistant. Of course, you can get rid of any trickery relying on my proof assistant as a programming language if you can actually just automate your computability proofs. If you have a tactic that constructs a Turing machine and proves it correct, you're golden. We don't have this. And I don't want to offend anyone, but I think this is because we still do not have good enough meta programming in any proof assistant. We've made a lot of progress in the last 5-ish years, mainly on the lean side, also in various, we've seen the hierarchy builder talk, Rocq LP, these kinds of things, meta Rocq that we will hear tomorrow. We've seen a lot of progress in proof assistants on meta programming. Nobody has actually taken up this challenge of doing automatic computability proofs. The people who have it are the HOL people. HOL4 essentially has this, Isabel Hall essentially has this, even though their systems are not computable systems. But if you can write down something computable, they can generate the proof. Yet, yes. Okay, let's skip this, let's go to the last slide because I think, yes, perfect. We're out of time. So conclusion. Computability theory proofs have a super high amount of invisible math, probably higher than many other areas if you really spell out the details. Lean, Rocq, Agda all allow keeping this invisible for computability because they're actually proof assistants. Like if you set up your things in the right way, you never see the ugly bits because you can hide them because they're actually programming languages, because you can hide this behind the fact that they are programming languages. We have this undecidability library in Rocq that covers almost all basic problems. We kind of run out of good student projects now, but that's it. A bit of an observation here, all of these were kind of self-contained. We had to give a student one paper, namely the paper that proved this undecidable, and then they could go and formalize it in this setting. So these were super ideal introductions into research. We know how to do computability theory, even with oracles based on axioms or automation. An open problem is how to do complexity theory. Again, the HOL4 people have a little bit on this. There is this work in Rocq by Fabian Kunze and people. There's the work in Isabel on the Cook-Levin theorem. There's more recent work, which was at some point on the slides, but I deleted it again, by Isabel, by Fabian Huch and Mohammed. Mohammed was here, I think, this morning.
Yeah, I am here online.
Yeah. Online, perfect, yes. On pushing this in Isabel even more, getting automation procedures for computability, but for now we have no solution how to do elegant complexity theory. We just have a solution how to do brutal complexity theory, which is already something. Good. Thank you very much. I'm happy to take it.
At the beginning, you mentioned Kleene Post, incomparable degrees, and I've seen your work on low symbol sets recently. I was curious if you can say something about what's more challenging with priority arguments and commutably enumerable degrees, or just generally about how C degrees work in the setting.
I think the thing that becomes a bit more challenging is that you need to talk about relative computability. And we have we have programming languages that are like programming languages in the Turing complete sense. They're on the level of Turing machines, but they have no built-in notion of oracles. So for oracles, you first need to define what it means to be oracle computable. And again, we have no good synthetic definition of what it means to be oracle computable, apart from kind of replaying the analytic definition of oracle computability on top of synthetic computability. Once you have done that, actually everything becomes fairly elegant again. And there's not too much work in the formalization side. These works we have on the line of computability there are very interesting, I think, from a perspective of constructive math. And they're interesting as formalization exercises. But I do think that from a formalizer perspective, we know what to do more or less. And we're kind of at the point where I would say, we just like crank it more and it will work more. But if you care about constructive math, it's super interesting because it's unclear what bits of classical logic you need.
And would infinite injury arguments still just be a matter of doing the more complicated thing?
Yeah, I think so.
Yeah, thanks for this really fun talk. Playing devil's advocate, I got to say, you're saying proving computability is hard, so we add an extra axiom that makes it easier. Isn't that kind of cheating?
Sure.
Do you think that's just fine?
I mean, if the axiom would be outrageous and not an axiom that people use on paper, I think maybe it would be actually outrageous. But in the end, formalization is always, I think nobody actually thinks we need to formalize everything. We need to formalize the bits and pieces that are interesting. And of course, we can burn student years on formalizing the boring stuff. But if we can get by the boring stuff, I'm happy to get by the boring stuff. And then later, if we can fill it in through like not axioms, that's perfect. I would never use this axiom for something that I can actually prove. But I once spent a month or so, very early in my PhD, on constructing a Turing machine that moves the tape to the leftmost point, the head to the leftmost point on a written tape. And I verified it, but it took me a month. And I was like, okay, not anymore. Since then I use the axiom. Everybody that can prove it in a more elegant way is like very much invited to just use a proof and not use an axiom. Until then, this works well, in particular because it does not get in the way. Like people can use their classical axiom as much as they want. There is no issue.
All about that. Isn't it kind of an issue that you can you get inconsistencies in Lean if you use non-computable functions?
Yes, and in lean, where you have the axiom, the full axiom of choice, if you're not careful, things go wrong. Because the axiom of choice, how it is written down in lean, relates a totality proof about relations to a type theoretic function. This is the one you cannot have. The one that relates, my Zoom here just crashed, but maybe that's okay. The one that relates a totality proof to just a functional relation, this one is fine. The one in lean is too strong. Like there you need to do explicit checks that your things are still computable. In the sense that they are not, like, you need to check that no non-computable annotations are used.
But I also thought that the idea of non-computable in lean was that it shouldn't affect your proofs.
That it should not
affect your proofs, right?
So
it kind of does if you add this axiom.
Non-computable will affect the proofs, yes, but it should not affect the proofs, indeed, but it will affect the executability and the computability of the program.
Right, but if you add this axiom about the church theorem, then it kind of breaks proofs, right?
Yes.
Okay, so yes. Okay, just to clarify. Yeah.
Angie has a question.
Can I ask a question?
Yes. Go ahead.
I'm online. I'm Mohammed, yeah. So I'm online. Yeah. Thanks for the great talk. I'm sorry I couldn't attend in person because I'm working on my own talk. Yeah, but I have. So can you say a few? So when you say complexity theory is an open problem, can you just say a few more sentences about that? Like why is it open? You formalized Cook 11, and you seem to have a way that works for all problems that are either that have a yes or no, or in general a bounded constant bounded answer. So
yes,
yeah.
So we have a solution on paper how to use lambda calculus to formalize complexity arguments, and it works well. And then step 2, we kind of all know that everything is true, is formalizable with enough time. But that's kind of a boring statement, because if the enough time is decades, then that's not interesting. So in the end, we are after finding ergonomic ways of formalizing things. And the stuff we have in Rocq does not allow ergonomic proofs. The work Fabian and Lennart had to do to get the Cook-Levin theorem, they had to work super hard because the extraction framework we have is wonky. Like it works if you know how to use it, and I know how to use it, but that's about it. So it's an open problem in the sense that we have no good proof automation yet anywhere to actually, I mean, you're working towards this, right? But
yes,
we have no full proof automation anywhere where you just take your function from the standard library, you press a button, you get a Turing machine. If we would have this, we would be much, much, much closer to working on complexity. We still have other problems you have to do, like O notations, bounding, and these kinds of things, which tend to be a bit annoying in proof assistance, but they turn up in other parts of math. Like essentially, we know how to solve them.
Okay, so open problem in the sense that we don't have a full proof automation.
Yes.
Yeah. Okay.
Or we don't have a synthetic way of doing it. If you could have a nice axiom which says something, that would also be cool. But nobody knows what a nice axiom is. But if you know how to do this, if you go to bounded subsystems of arithmetic, these kinds of things, and you use realizability.
Yeah.
But we have no proof assistance for these things. So again, from a formalization perspective.
Yeah. Oh, I mean, yeah, I think time is up, but I will definitely just continue talking to you tomorrow, I hope. Yeah.
Sure. Yes.
Right. Yeah, thanks.
So if you had a meta program providing you instances of church thesis, as you presented it, so could you replace your axiom?
Absolutely.
Use it only a finite number of times?
Church's rule, the thing that they proved for systems, in the 40s, like essentially that was the notion of a meta program back then. Like the point is you have like a proof transformation that's actually effective, and they say it like this, that's a meta program. So if somebody implements this meta program, you're good. Implementing this meta program is also exactly the automation tactic. Like that's all the same thing. If we would have this, many things would be simpler.
Could you replace it
like
directly?
Yes. Yes. There's nothing deep, kind of, in a sense.
Okay, let's thank the speaker again. That was the last talk for today.